So I'd say it's about 70% and maybe 30%, somewhere. Let me show you where we get this number of 85.47. Mass, which is that last remaining number on the periodic table. And hopefully you'll sleep better at night knowing what that number is used for. We'd use what's called a mass spectrum. And this is a test where we basically take a sample of an element and separate the different isotopes according to mass. And the heavier ones would separate out, and basically we get a relative count of the abundance of those elements. And so for rubidium, it's actually element number 37. There are two isotopes that occur in nature. There's rubidium 85 and 87. And if there was an 88, it would show up here. Okay, and so we get this relative number. Now, first thing that you notice is there is intensity. This is not percent on the left, not the percent abundance, but it's the intensity. And so to get the percent, I would say we would need to add these two numbers. I would call that about 40, and I would say that's about 100. And so the percent would be 100 divided by 140, which is about 70%, okay? So if a mass spectrum is in percent, you're great, but if it's in intensity, you have to calculate percent. So I'd say it's about 70% and maybe 30%, somewhere about that. So this is the relative abundance of the isotopes of rubidium. Now, what do we do with this? We are going to calculate atomic mass, okay? So let me just give you the definition here. Atomic mass is a weighted average of the naturally occurring isotopes. So for rubidium, those are the isotopes, and we're going to do a weighted average. So can you see that the one that is more present more abundantly would influence the average more than the other? So if we have mostly rubidium 85, do you notice that the weighted average is slightly above 85 and not toward 87? If it was 50-50, if I had half 85 and half 87, the weighted average would be 86. So let me show you where we get this number of 85.47. So these are the actual percent abundances of the two isotopes, and these are the actual masses. So to calculate the atomic mass, here's what you do. You take the percent abundance and write it as a decimal. And then you're going to multiply times the mass of that isotope. Okay, and then we're going to do the same thing with all the other isotopes. So the percentage as a decimal times the mass. And if we had 3 different isotopes, we would write them all and add them up. Some elements have 4 or 5 more common. And guess what you get when you use the calculator to do this? You get 85.47 AMUs. So, mystery solved. Where does atomic mass come from? This little number right here. It is the weighted average of all the natural occurring isotopes. Okay, so somebody did this for you. You don't have to do the math. Okay, someone did that. And if you picked up one atom of rubidium, would it have this mass? There's not a single rubidium atom that has that mass. It's either going to be this one or this one. But we can assume that that is a good average mass. Okay, so that's how we use atomic mass. Now let me show you one more trick. You can tell a little bit about an element based on the atomic mass. Okay, so take a look at magnesium. Atomic mass 24.31. Now, we looked it up. There are 3 naturally occurring isotopes. Which one do you think is the most abundant that would give you an average of 24.31? You guessed it. It is magnesium 24. That is the most commonly abundant isotope of magnesium. And then there's just a little bit of 25 and 26 that just tweak that average up above 24. So I hope that gives you a thorough understanding. We are going to use that atomic mass a whole lot in the rest of the semester of chemistry.